We're now on to part 3 of waves, and we're going to look at refraction. And refraction essentially refers to the speeding up or slowing down of waves, so you are changing the speed of the wave. Now, light travels the fastest in a vacuum. It travels at the speed of light, which is 2.998 times 10 to the 8 meters per second. And the speed of light in air is almost the same as c. But when light passes into a more optically dense medium, such as glass or water, it slows down, it's refracted. And as a result of refraction, as a result of the slowing down of the wave, the light is bent. The absolute refractive index of a material, which is denoted by the letter n, is equal to the speed of light in a vacuum divided by the speed of light in a material. And we can also have something called the relative refractive index of light, and the relative refractive index of light going from material 1 to material 2 would be equal to the absolute refractive index n2 divided by the refractive index n1. If we look at Snell's law, we can see that we have a ray of light coming up through a more dense medium, for example water. The more dense medium is denoted by the refractive index n1, and it's passing into a less dense medium whose refractive index is n2, and you can see the angles of the light away from the normal. And Snell's law says that n1 sine theta 1 is equal to n2 sine theta 2. And it's interesting to note that if light passes from a more dense medium into a less dense medium, then it will be bent away from the normal. Let's consider what happens in total internal reflection. Okay. So here we have our light ray, again coming up through a more dense medium such as water, and it hits the interface between the water and the air, and it's refracted, it's bent away from the normal. Now at the critical angle, which is shown in the middle picture, the light will not actually emerge into the air, but it will track along the interface between the air and the water. And when that happens, the incident angle is actually called the critical angle. And beyond the critical angle, that's when we get total internal reflection. No light will enter into the air, it will all be reflected back into the water, and the angle of incidence will be equal to the angle of reflection in that particular case. So at the critical angle, if we substitute the sums into Snell's law, we can see that n2 sine of the critical angle is equal to n1 sine of 90 degrees. But n2 sine c is equal to n1 multiplied by 1, because the sine of 90 degrees is 1, but n1 is also 1. So we can say that n2 is equal to 1 over sine c. So let's look at some applications of total internal reflection, and we're going to look at optical fibres. So here we can see that total internal reflection is used in an optical fibre to pass the light ray down that fibre. There are advantages of sending information in this way. The light has a higher frequency, so it has more energy, so it can carry more information than perhaps an electrical signal could in a wire. And also the light doesn't heat the fibre up, so there is almost no loss of energy as heat, and there is no electrical interference. And that completes the end of part 3.
Created using Powtoon.